Hi, today we are going to look at hybridization. We are going to learn Today we are going to learn the concept of hybridization. Now to learn the concept of hybridization, let's look at an example of CH4. CH4 is generally known as methane. So we look at the example of CH4, and what will hybridization tell us? Hybridization will give us the molecular geometry of CH4. Now to know the molecular geometry of CH4, first let's write the electronic configuration of carbon. Now we know how to write the electronic configuration of carbon. First we need to know the atomic number of carbon. Atomic number of carbon is 6. Now the first two electrons will go into 1s orbital. So the first two electrons will go into 1s orbital. So let me draw the orbitals also, orbital diagrams also. So this is my 1s orbital. Let's say this is my 1s orbital, and I have two electrons with opposite spin. So this is my 1s2. Now the next two electrons will go into 2s orbital. Now the next two electrons going into 2s orbital. So this is my 2s orbital, and there will be two electrons here, same with the opposite spin but paired electrons. So these two orbitals have two electrons each, and they both are paired. Now my next 2p orbital, now 2p subshell has three orbitals. 2p subshell has three orbitals. Let's say px, py and pz. This we have already seen in atomic structure when we spoke about orbitals. But my 2p subshell has three orbitals, px, py, pz, and each one can have two electrons each. But how many electrons we are left with? Because there are already 4 electrons in 1s and 2s orbital, so we are left with only 2 electrons. So I'll write it as 2p2. So these two electrons will go, one here and one here. So these are the two electrons which we have. Now if I have to draw this, so let's say if I have to draw all this in the space, how will I draw it? So let's say this is the nucleus of carbon. I have 1s orbital here, so it has some two electrons. Now I have 2s orbital here. Let's say I have, so this is kind of a sphere, and here I have two more electrons. Now if I have to draw p orbitals, for that let me just draw the axis through the nucleus. So this is my py, this is my x, and this is my z axis. So this is my axis. Here if I have to draw these 2p orbitals, so the 1s had 2 electrons here, the 2s had 2 electrons here. Now if I have to draw the p orbitals will look something like this. Here I have py. If this is the y axis, then this is py. Then this is my px, and this is my pz. Now if I say this is my pz, this is my px. Now if I say that there are two electrons in p orbitals, so let's say they are in px and py, it can be anywhere in these three. So let's say there is one electron in px and one electron in py. So our carbon will look something like this. So we have 2 electrons in 1s orbital, 2 electrons in 2s orbital, and 2 electrons in 2p orbital. Now what happens when it is trying to bond with hydrogens? What is the electronic configuration of hydrogen? Hydrogen has an electronic configuration of 1s1. So there is one electron, and which is there in 1s orbital. So in 1s orbital there is an unpaired electron. Now if carbon has to bond with 4 hydrogens, it should have 4 unpaired electrons here. So then they'll bond with the hydrogens, 4 hydrogens will bond with the carbon. Now let me tell you what happens when carbon is trying to bond with hydrogens. So carbon had 1s2, 2s2 and 2p2 electronic configuration. So I had 2 electrons here. This was 1s2, this was 2s2, this was 2p2. Now in the case of bonding, what happens is this electron actually gets excited, and we say that it goes into the p orbital. It gets excited and it goes into the p orbital. So this will go into the p orbital. So let me erase it from here, and this will go into the p orbital. So now carbon will look something like this. So this is the excited state of carbon. This is called the excited state of carbon, where one electron gets excited from 2s orbital to 2p orbital. Now in case of hybridization, what happens is whenever carbon is trying to bond with hydrogen, it does not bond directly with these electrons. These orbitals, this 2s orbital, let me draw it here. My 2s orbital will look something like this. This 2s orbital, now I have 3p orbitals. 3p orbitals are something like this, and this. This 1s orbital and these 3p orbitals, what happens is they intermix together. They intermix together and they give me 4 hybrid orbitals. 4 hybrid orbitals of equivalent energies. 4 hybrid orbitals of equivalent energies. So what do we say here is these 4 orbitals, this one, and these 3, this one, and this one. These 4 orbitals, they intermix together and they give me 4 hybrid orbitals of equivalent energy. So these are my 4 hybrid orbitals, and it will have 1 electron each, and these are my 4 hybrid orbitals. These all 4 orbitals are intermixing together and giving me 4 hybrid orbitals, and they'll be termed as sp3 hybrid orbital, because we had 1s orbital and 3p orbitals intermixing together. This is my 1s orbital, and this is my 2, 3, 4 orbitals intermixing together. That's why there is 1s, s is 1 here, and p3, sp3 hybrid orbital. So each of these orbital will be termed as sp3 hybrid orbitals. So this is my 4 sp3 hybrid orbitals. 4 sp3 hybrid orbitals. Now, what will be the shape of my hybrid orbital? My hybrid orbital will look something like this. It will have a bigger lobe. It will have a bigger lobe and a smaller lobe and a smaller lobe. It will have a bigger lobe and a smaller lobe here. So my all 4 sp3 hybrid orbital will look something like this. This is my sp3 hybrid orbital. sp3 hybrid orbital. This is my sp3 hybrid orbital. Now if I have to arrange these 4 sp3 hybrid orbitals of carbon in space, how will I arrange it? So let's say this is my carbon. So this is my 1 sp3 hybrid orbital, and let me change the color here. This is my other sp3 hybrid orbital, and the third, let's change the color. This is the third sp3 hybrid orbital and the 4th sp3 hybrid orbital. Sorry for this. This is the 4th sp3 hybrid orbital. So they arrange themselves in a geometry called tetrahedron. We know about this geometry. We have learnt about this in VSCPR theory. Tetrahedral geometry is a geometry where all the angles all the bond angles are 109.5 degree, 109.5 degree approximately. It looks something like this, where these all are in 3D space. It is going inside, and the angles are here 109.5 degree approximately. So whenever these hybrid orbitals are arranging themselves in space, they want maximum angle because they'll face the least repulsions in that case. So this angle will be 109.5 degree approximately. So here I have got four hybrid orbitals of the equivalent energy, and I had one electron each in each sp3 hybrid orbital. So I'll have one electron here, I'll have one electron here, one here, and one here. Now this is my carbon. This is how my carbon looks like. If I have to bond this with hydrogen had one s1, so only s orbital had one electron each. Now if it has to bond with hydrogen, my hydrogen will look something like this. So it will bond with these hybrid orbitals, and it will share its electron with the carbon. So this is my one of the hydrogens, and the one electron of hydrogen, the other hydrogen, and this one last. So these are my four hydrogens, and this is how my CH4 molecule will look like. This is how my CH4 molecule will look like. It will have a geometry of tetrahedral. It will have a tetrahedral geometry. Now from this, so if we have to summarize this, what did we get to know from hybridization? So the orbitals involved here, the orbitals involved in hybridization, I had one s orbital and three p orbitals. This is 2s, this is 2px, this is 2py, and this is 2pz. So all these orbitals should have nearly the same energy to hybridize together. The hybridization will only happen whenever these orbitals will have similar energy. And the second point here will be the number of hybrid orbitals. Here the number of hybridizing orbitals were 4, 1, 2, 3, 4, and the number of hybrid orbitals we got were also 4. So the number of hybrid orbitals is always equal to the number of hybridizing orbitals. The next point here is the hybrid orbitals are all equivalent in energy. They all are equivalent in energy. They all are equivalent in energy. So now we have looked at CH4. In the next video, we'll look at the formation of pi bonds also using hybridization. And there are different types of hybridization. This was just only the one type. This is sp3 hybrid. This was sp3 hybridization. We'll look at the other types of hybridization like sp and sp2 hybridization in the next video.